Good afternoon, my dear students. Now I will explain one problem of Lorentz series expansion. So find the Lorentz series expansion of fz is equal to minus 1 by z minus 1 into z minus 2. Valid for three problems are there. Number 1, mod z if the closed curve mod z less than 1. And second problem is mod z lies between 1 and 2. And the third problem is mod z lies between and 2 to infinity. So first we take the given function fz, first partial fractions, take it, then we get fz is equal to 1 by z minus 1 minus 1 by z minus 2, and the singular points are, therefore the singular points are 1 and 2, two singular points for fz. This is fz. And first problem, let d1 be the domain mod z is equal to less than 1, mod z less than 1. That is, mod z less than 1 means mod z also less than 2. Mod z less than 1 means less than 2 also. Therefore, mod z less than 1 we can write, and mod z by 2, mod z by 2 also less than 1. If we take fz 1 by z minus 1 minus 1 by z minus 2, uh, here z is less than 1, mod z is less than 1, therefore we should write 1 minus z type. Therefore take minus 1 by 1 minus z plus, here already minus is there, minus into minus plus, plus 1 by 2 minus z. Take 2 common here, 2 1 minus z by 2. 1 z by 2 also less than 1. Here z by 2 also less than, z by 2 also less than 1. So now expand this part. Since z is less than 1, we can expand it. Therefore write it in the numerator. Here also take 2 common and write it in the numerator. We get this function and expand this function. 1 minus z whole power minus 1 is this expansion, and 1 minus z by 2 whole power minus 1 means this expansion. And this is the Lorentz expansion, minus 1 by 2, and simplify this function, minus 3 by 4z plus 7 by 8 z square, and so on. This is the Lorentz expansion of fz if the domain mod z less than 1. And for second problem, D2, the domain is mod z lies between 1 and 2. Here first take 1 less than mod z, that is mod z greater than 1. Mod z greater than 1 means here 1 by z, take 1 less than, here 1 less than mod z, therefore 1 by mod z is less than 1. We should write it is like less than 1, and also 1 by here, and mod z less than 2 means z by 2 less than 1, z by 2 less than 1. Our fz is equal to 1 by z minus 1 minus 1 by z minus 2. Therefore we should write it as 1 by z type, 1 by z type. Therefore 1 by z, take common z. Here we get 1 minus 1 by z minus, for this z by 2 z by 2 type ka. Therefore we take common 2. 2 common means minus 2 common. Therefore 1 minus z by 2. Here z by 2 less than 1. Therefore we can write 1 by z into 1 minus 1 by z whole power minus 1 plus 1 by 2 into 1 minus into minus plus 1 by 2 into 1 minus z by 2 whole power minus 1. Since 1 by z, here since 1 by z less than 1 and also z by 2 less than 1, therefore we can expand these functions. Therefore we can do expansion. After expansion and simplification we get Lorentz series. For third problem, For third problem, the region is mod z lies between 2 and infinity. 2 less than z means we can write 2 by z less than 1. 2 by z less than 1. Okay, 2 by z less than 2 less than mod z means here 1 by z less than 2 by z less than 1 means 1 by z also less than 1. 1 by z also less than 1. Consider the function. So 1 by z type and 2 by z type, and 1 by z is less than 1 and also 2 by z less than 1. So expand these functions. Okay, here we get fz. And for second problem, like this, expand here the domains are. Write two Lorentz expand series. The function is 1 by z into 1 plus z square in certain domains. Satisfied. So this is the simple problem. Okay, we can do. We can do. Next, the topics are absolute, conditional, and uniform convergence. Here, the series, let the series an summation an z minus z power n be convergent power series in some circle of convergence. That is, the circle is mod z minus z0 is equal to r. If this is convergent, if the modulus or absolute value of the series are also convergent, then the power series is said to be absolutely convergent. If it is not, if the absolute value is not convergent, then this series is called, this given series is called conditionally convergent. Okay, my dear student, this topic is completed. Thank you.